Alrighty, my friends, we're going to show that the freezing of water is spontaneous, which means it occurs without additional energy at negative 20 degrees Celsius and 1 bar. And there's a variety of different ways to do this. I have other ways, you can find them in the description below, but in this video, we're going to use the fundamental equation of chemical thermodynamics, which is delta G equals delta H minus T delta S. Change at, say, 0 degrees Celsius is the same at negative 20 degrees Celsius. So this is positive, which means it takes energy to melt water. This is a fusion, so we're melting water. It takes this much energy per mole to melt water at 0 degrees Celsius. We're assuming if we were to melt the water at another temperature, it would take the same amount of energy per mole. And same thing with freezing. Regardless of the temperature, we get the same amount of energy released from the water when we freeze it. That's what we're assuming. It does depend on temperature, but we're assuming it doesn't. So if that's the case, and we'll add a little bit of notation here, bear with me, we want the change in freezing, and this is the change of Gibbs energy G at negative 20 degrees Celsius, which is 253 Kelvin, and this is the under standard state, so that's what this superscript here means. It's a constant pressure of 1 bar, that's what it means. This is at 1 bar, and it's in its pure form. Is approximately equal to the enthalpy change at 0 degrees Celsius, because the enthalpy change for freezing water doesn't depend on the temperature, is what we're assuming anyways. And this process is occurring at negative 20 degrees Celsius, which is 253 Kelvin. And then the same thing, we're assuming that delta S doesn't change as well. Now, to get this change in entropy, we're going to look at 0 degrees Celsius. So at 0 degrees Celsius, 273 Kelvin, the liquid and solid phases are in equilibrium. And if they're in equilibrium, then the change in Gibbs energy is 0. Now, we can use this exact same equation here and plug in 0 for delta G at 0 degrees Celsius to get an expression here. And if we solve for delta S, then we have an expression for the entropy change of freezing our water right here. And we can plug this into our equation that we have. And now we have everything in terms of the enthalpy change, which is good because we're given enthalpy change value right here. Now we want to know the enthalpy change of freezing, but this is of melting. And fusion could be of freezing as well, but we know this is melting because it's positive. It takes energy. You put energy into the water and it melts. You take energy away from the water, it freezes. So the enthalpy change of freezing equals negative the enthalpy change of melting, of fusion. And from here, we can just plug in the values and plug it into our calculator, which gives us a Gibbs energy change of negative 0.440 kilojoules per mole. It's negative, which means it's spontaneous. And if it's spontaneous, then the total entropy change of the universe is greater than 0. We can solve for the entropy change of the universe for fun, which is equal to negative delta G over T. This equation comes from the second law. I can derive this if you want me to, just let me know. If we plug in our values for delta G, this is positive because this negative cancels out with this negative here, and we have a positive entropy change of the universe, which means the process is spontaneous. Cool beans. All right, y'all, hang in there. Good luck on your midterms, your final exams, and all that stuff. I know thermodynamics is a challenging course, but the more problems you do, the better you'll get. Problems, problems, problems. Hang in there. I'm with you every step of the way. Cheers.